is about the continuity of derivatives. Okay, we have this theorem. Continuity of derivatives. Okay, this theorem says that if we have a function f that is real undifferentiable, in a closed interval ab, and we suppose that f prime of a is less than lambda less than f prime of b, then there exists a point C in AB such that the derivative at C equals lambda. Okay, so what are we actually, let me add a second part. In particular, the function f prime, the derivative, cannot have simple or what is the same, removable discontinuities. Okay, there is a comment here. But f prime could have discontinuities of the second kind. Okay, a jump discontinuity or an infinite discontinuity. Let me take out the parentheses. There we go. Okay, so let's be clear. What are we saying here? Here, what we are saying, it's that similarly to what happens to continuous functions. The same way a continuous function assumes all the values in between two given values, the derivative also does that. Okay, so if you have a function that is a derivative, it's not going to suddenly miss one point and continue as if nothing happens, okay? This cannot be a derivative. If you think about different examples, you will see that either the derivative is continuous. Okay, let's think about, you could think about a function like this, right? That when you look at the derivative, first is negative, then is 0, then is positive. Okay. But it's going to be continuous. Okay, it's actually going to be a straight line because what I drew was a parabola. Okay, but we could think other functions. We could think, for example, the absolute value of x, okay, where the derivative is going to have a jump. It's going to go from -1 to 1. Or we could think, let's say, well, it could be the square root of absolute value of x would be something like this. Okay. In this case, the derivative is not going to have it's not going to be defined at 0. It will blow up at 0. Okay, because it would be 1 divided by 2 square root of x. Okay, and then you need to adjust for the sign. But anyway, you see what we are saying here, that these discontinuities are of the second kind. There is no discontinuity like this one here that is just removable. that you could just shift a point and fill the gap. I'm just realizing the derivative in this case is negative on the left of 0, okay, because notice here the slope is clearly decreasing, okay, it decreases to negative infinity. So in this, on this side would be -1 divided by 2 the square root of absolute value of x. Okay, now it's correct. So to prove the theorem, let's go back to the theorem. We actually only need to prove the first part, okay, because the second part is a consequence of what we proved in the first. Okay, so let's focus on proving the first part. Let me copy paste. So we want to show that if f is real differentiable in AB and f prime in A and f prime in B bound lambda, then there exists some C such that f prime in C equals lambda. Okay, so let's get to it. Here, what we are going to define is g of t, which is f of t minus lambda t. Here we want to work with the derivative. So g prime of t is f prime of t minus lambda. You see what I did here? We have lambda that is related to f prime. So I define this g so that we can relate the derivative with lambda. So g prime of a is going to be f prime of a minus lambda, which we know it's negative, but g prime of b is going to be f prime of b minus lambda, which is positive. So see what happens here. We have our g prime, which is negative on the left, positive on the right. So g prime must be 0. Okay, this is intermediate value theorem. G prime, well, let me write it down carefully. There exists C in AB such that g prime of C equals 0. But then because g prime is f prime minus lambda, f prime of C equals lambda. And that is what we wanted to show.